It's my pleasure to welcome you to this year's edition of the Smalley Lecture in Materials Science and NanoEngineering, which will be presented by Professor Stanley Whittingham. It's a shame there wasn't more interest in the talk, but it's great to see you all here. Thank you again for coming. So Rice has been a leader in advanced materials research and education for years, and as we work to kind of propagate that forward and continue it and even grow that, engaging with thought leaders in spaces that are really important for society today is a critical part of that, and our speaker represents that very, very nicely. So I'm going to serve as our MC this morning, and I want to give you a little overview of the event. So in a few moments, I'll hand it over to Professor Jun Lo from Materials Science and NanoEngineering, who will give us a brief introduction to Professor Whittingham. We'll then kick off the lecture. We'll have Professor Karen Lenzano, who's the chair of Materials Science and NanoEngineering, join us afterwards for a few words. We'll then open it up for questions from the audience. And then afterwards, we invite everyone to join us in the lobby outside the hall, where there'll be some drinks and refreshments. And since we had the Nobel Prize on our minds, we've also arranged for Professor Smalley's 1996 Nobel Prize in Chemistry to be on display. So if you want to get a selfie with the Nobel Prize outside, you're welcome to do that or just take a look. But with all that said, thank you again for attending. Let me hand it over to Professor Jun Lo.
All right. Good morning, everyone.
Good morning.
Welcome. So, ladies and gentlemen, it's my great honor to introduce a true pioneer in the energy storage technology, Professor Stanley Whittingham, here today. Born in England and got all his degrees from the University of Oxford. Professor Whittingham is a distinguished scientist whose groundbreaking work actually transformed how we power our world. In recognition of his outstanding achievement, we are really thrilled today to invite Professor Whittingham to deliver the annual Smalley Lecture here at Rice University. This lectureship was made possible by the generous gift from Professor Bob Huggy and Professor Wade Adams. This lectureship is basically honoring Nobel laureate Richard Smalley's legacy for scientific excellence. As a professor at Binghamton University, Professor Whittingham has dedicated decades to advancing battery technology. His pioneering research back in the 1970s while working at Exxon led to the development of lithium-ion batteries, an innovation that powers everything from the smartphones everybody has and the electrical vehicles. So his very important discovery was to discover the intercalation electrodes, which laid the foundation for rechargeable lithium-ion battery. His contribution has been widely recognized, culminating in the 2019 Nobel Prize in Chemistry, which he shared with John Goodenough and Akira Yoshino. Beyond his research, Professor Whittingham also leads the key energy initiatives, including the US Department of Energy and Northeastern Center for Chemical Energy Storage, working towards more efficient and sustainable energy solutions. Professor Whittingham's legacy is not just in his discovery, but also in the lasting impact of his work on global energy storage and sustainability. So please join me in welcoming Professor Stan Whittingham.
Thank you very much. You can hear me okay? Good. So what I want to do is give you a little bit of background about lithium batteries. I promise there won't be too much chemistry. So I know engineering students don't like chemistry too much. I taught freshman chemistry for our engineers at Binghamton for many, many years. And I can assure you, engineers are much nicer to teach than pre-med students. Engineers, a B is good. Pre-med student, why didn't I get an A+? So what I want to do is really go back a little bit in history and now ask a question. Is there anybody in this room who does not have a lithium battery on them right now? No? So you all understand how they work, what's behind them, and everything else, right? So when we got the Nobel Prize, the equivalent of PBS in Sweden spends about 2 days on campus. They came to Binghamton, came to Austin, and went to Japan. They said, this is the easiest ever program they did. Everybody has one. They had to do one on quasi-crystals. They said that was a nightmare to do, trying to explain that for the general public. So let me start at the beginning. I show you 2 buses here. These are most recent ones, and I showed these intentionally. One is Vietnam is going very electric. So these are VinFast buses. And on the right-hand side is a bus from Alabama A&M University. That university, a good red state, only has electric buses on campus. So they really pushed to make it go. The bottom you see the quote from the Nobel Committee. And my message to everyone is, we've talked enough, now we have to have action and make things move forward. So let me just go to the next slide. I want to emphasize to everyone, it was then ESSO. And it was ESSO who got us into this business, ESSO who got us into renewable energy. And things have obviously changed since then. But at that time, Exxon was the largest manufacturer of solar photovoltaic cells in the United States. They did all the nuclear reprocessing in the United States. So they're very much more than an oil company. Later on, they bailed out, but now they are drilling for lithium in Arkansas. Right down the street here, they're now making the carbon for the anodes of lithium batteries. And they used to make the separators for lithium batteries as well. So they're still being very involved, and they're getting more and more involved. So in the center there is a copy of the original patent that was filed. And on the right-hand side, you'll see 2 of the original batteries. We made it Exxon one. The paperweight there has a little solar cell, lithium battery, and a clock. The only bit that's starting to fail is the clock. But this one is almost 50 years old. It still sits in my house, and it still works well, particularly on a sunny day. So very well-made lithium battery will last forever. Beneath that are some cells we made for electric vehicles. So remember, back in the 1970s, there was no such things as iPhones, laptop computers, any of those things. What we needed was batteries for electric vehicles, and Exxon was interested in making electric vehicles. And they bought an electric motor company, and they talked to Toyota in those days about EVs. So that's when we talked to the EV show in Chicago. It's about 6 inches by 4 inches, about an inch thick. Largest rechargeable lithium-ion batteries till about 10 or 15 years ago. So that's the beginnings. The bottom right, you'll see the single crystals we used to use, and I'll come back to that a little later. So that's where we stood in the 70s. This is where we are now in transportation. The forklift truck there is by Raymond. The one underneath, the bus underneath is BAE Systems. Both those are in the Binghamton area. So BAE Systems does all the electrification for buses in Binghamton for worldwide. The little car there is one my wife and I rented in Bermuda for our 50th anniversary. And it was about the 3rd or 4th EV they had on Bermuda. Tourists are not allowed to drive cars on Bermuda. You have to drive scooters. But they passed a bill to allow electric vehicles, so we rented this one at some exorbitant price. And they said, if you drive to the other end of the island, make sure you recharge it before you come back, because it won't make it back. So we drove to the other end of the island, went to the recharging station, and they were still building it. So fortunately, we found a hotel that had a small charger. We had dinner, and we got enough electrons in so we can get back to the hotel. But my wife says, no more EVs. Range anxiety is real. Next to that are two fully electric trucks. These are at Packard, north of Seattle. The first one is a 16-wheeler, fully electric. And next to it is a garbage truck. Garbage truck is perfect electric vehicle. The stop, go, raise and lower the whole day long. And I got to drive both these around their track. And the only thing they said about the big truck is don't go above 60 miles an hour. And please don't go up the slopes on the corners. And no, take it wide on the corners as well. So you don't, but no, these big trucks have acceleration just like a small EV. Put your foot down, as it were, and off they go. Beneath that, I'll show you pictures of 4 London buses, which I took standing at the end of Oxford Street a few years ago. So London is trying to decide what clean vehicles to use. The large one is a fuel cell bus. Next to that is the hybrid bus and the fully electric bus beneath it. On the right-hand side is what they call a clean diesel. I'm not sure what that really is, but it looks like when I was last there a few weeks ago, they're going more to the hybrid buses than the fully electric right now. But there's a huge move going on. So that's transportation. This is grid storage. This is big but fairly quiet in Texas. So there's a lot of grid storage facilities here. They don't publicize it much, but people need to realize I think Texas has more renewable energy than any other state, despite what politicians may want and say. Ranchers say it's much easier to make money from wind turbines than from herding cattle everywhere, and much less work. So huge activity there. So on the right-hand side, I'll show you a wind farm from West Virginia. This is more than 10 years old. Beneath that is one of the first grid storage facilities in the United States. That was in Binghamton. This uses lithium iron phosphate. It's about 2009 it got going. They put it next to a coal power plant. Within 1 month, coal power plant was turned off. It's never come back on again. So a small storage facility can do everything what a peaker power plant can do. That particular storage facility moved because we had a huge flood in Binghamton in 2011. These trailers floated. They fixed them. Then they went to the state of Ohio because they could make more money. And this is why people like lithium ion. You see, they're trailers. You can put them on the back of a truck and just move them. Right now, these are all in Puerto Rico. After the 2 hurricanes there, they're now to stabilize the grid. So these are well over 10 years old, and they're still working. And we're proud to say these particular ones were made in America by Americans. Maybe the last ones, but they were by Yetming Chang's company. In the middle, there's one of these typical huge solar facilities now. This one's in the desert in California, over 3 gigawatt hours of storage. So, no, in the right place, if this one burns, no one will see it for a while. Unlike the one south of San Francisco, you probably saw caught fire a few weeks ago, and they lost about 40% of it, and they closed the highways. So you're going to have huge facilities, put it more remote so it's not an issue. But this is where things are going. Batteries are not the largest means of storing electrical energy. The largest means by far is pumped hydro. I'm not sure there's much in Texas, but the Tennessee Valley Authority has a lot, New York has a lot, Pennsylvania has a lot. They're mostly used for regional, no. We have lots of excess power spring and autumn. We need lots of power in the summer and winter. So you fill them up in the spring and fall and use the power during the summer and the winter. Batteries can never do that. So just in case there's anybody who doesn't understand what a lithium battery is, or doesn't understand what the word intercalation means, find an old dictionary, look up intercalation, and it'll talk about the leap year. You intercalate February 29th into the calendar one year, then next year you take it back out and the calendar looks just the same as it used to. So in the chemical terms, it's the same thing. We're doing a chemical reaction. You put something in the structure, you take it back out, and you cannot tell that you've done that. And that's why these batteries can be rechargeable. You can put atoms in and out of a lattice and not significantly change that lattice. It may expand by 5 or 10%, but you're not destroying the lattice and rebuilding it. So in today's lithium-ion batteries, you have intercalation electrodes on both sides. So you'll see on the left-hand side, the anode here, this is now graphite, the same stuff as in your pencils. And the lithium ions, the green ions, go between the sheets of the graphite when it's fully charged. When it's discharged, the lithium ions go through the electrolyte, that's what's in the middle. If you've got a lead acid battery in your car, that's the lead acid, the liquid water there. On the right-hand side, you then have another material where you can intercalate those lithium ions as you discharge it, and the electrons go through the external circuit. The key to making this work is these three components must only react electrochemically, not chemically. And the challenge is most batteries are thermodynamically metastable. In other words, you're relying on protective films to stop them corroding. So we'll get into that a little bit. So the electrolytes are organics, mostly, because obviously you can't have water there with lithium, and then there's various salts in there. So this is a little history. Said it all started with ESSO back in 1972. Maybe 10 years or so later, they decided there wasn't enough money to be made in batteries and fuel cells and all these things, so they sold all those businesses. It turns out that ESSO licensed it to a European company, a Japanese company, and an American company. The American company was Ever Ready, had a joint program with Sony, and that's how the technology leaked to Sony. I think Exxon licensed the technology to Sanyo. So now you had two Japanese companies competing with each other. So this happened in 71. Sony commercialized lithium batteries in 1991. And I want to make the point, they were the first company to successfully launch lithium batteries, which means they made money. Another number of other companies, including Exxon itself, plus Canadian companies, made a lot of lithium batteries. The lithium batteries have a tendency of catching fire, so they had problems. What made these safe is you use graphite to store the lithium, so there's no lithium metal in the lithium-ion battery. That's why it's called lithium-ion. There's only lithium ions. When things go wrong, it's when you plated out lithium metal, and then it catches fire and does other nasty things. So we started out with lithium metal. We realized there were issues. So any semiconductor person in the audience will know you don't want to get lithium anywhere near your semiconductor. It reacts with everything. What we switched to was using aluminum. So lithium reacts with aluminum at room temperature, 1-to-1 alloy, and that works fairly well. But it doesn't last very long, because lithium, going to lithium aluminum, you're building a new structure, then destroying it, building it, and so on. So that's when Akira Yoshino in Japan started using carbons, one sort or another, and found you could intercalate lithium into the carbons. So that's where the graphite anode came up. That is what's still used today in essentially all lithium-ion batteries. The graphite is half the volume of the cell. You need 72 grams of carbon to store 7 grams of lithium. So if we want to increase the energy density, we've got to get rid of that. So a lot of effort now to go back to lithium, and I'll come back to that in a minute, and that's why I'm in Rice. The last 2 days, we had our battery 500 review meeting here with DOE, and that's looking at lithium metal itself. There's still issues with lithium metal, so commercially people are going to things like tin and silicon. Both of these react with over 4 lithiums. So they're very good from a volumetric point of view. So a lot of effort there. On the cathode side, we started with titanium disulfide. You may say, why titanium disulfide? It's a nice layered compound. All sorts of ions go in there, any electron donors, lithium, sodium, potassium. You can put long chain ammonium, things in there like C18, nitrogen. And the interest initially was electron donors. They put electrons into the lattice, change the superconducting properties. So that's why we were looking at those. Tantalum disulfide was the best one. You can't use tantalum in a battery. So when we discovered these reactions, we switched to titanium, and that's what we used. Has voltage about 2.5 volts. John Goodenough was then at Oxford, read our papers. He was looking at lithium cobalt oxide for its magnetic behavior. And he said, hey, these have the same structures. I can do the same thing. Now, no, John is not a chemist. He was professor of inorganic chemistry, but he didn't know any chemistry. So he had not been told that cobalt-4 does not exist. So he decided he would take the cobalt out of lithium cobalt oxide, and he managed to do it. But no, nobody at Bell Labs or at Exxon had tried that. But they try things that may work. The point is they're all metastable. So the cobalt is 4+. When you take the lithium out, it doesn't want to be 4+. It wants to lose oxygen, and that brings up some other issue. Cobalt is too expensive, so then the field went to a mixture of nickel, manganese, and cobalt. Or Tesla used to use nickel, cobalt, and aluminum. Same structure, everything else. But again, still very expensive. So John was trying to make some phosphate materials. They were called nasicons. The students couldn't make them. They always got some impurity in there. So John spent his summers in New Hampshire, away from the Texas humidity and heat. And he came back and said, where's this compound? Well, we couldn't make it. We got this impurity. Well, he said, make the impurity then. And that was lithium iron phosphate. So they invented lithium iron phosphate, published it, then tried to patent it. They got the US patent, but all the rest of the world, they lost the patents because they'd pre-published. So this is a message to everybody in the audience: patent first, don't. And the publication was just a title of an abstract for a meeting. So he pushed that very out. I'll come back to that material because that's now a hot item, because in America we got lithium, we got iron, we got phosphorus, and clearly we got oxygen. So we got all the minerals we need there. We don't have the nickel and cobalt in the US. So from lithium iron phosphate, it's now interested in lithium manganese phosphate. It has a higher voltage, but both these you'll see in a moment are very low energy density compared with the oxides. So we decided if we want to increase the energy density, why don't we put 2 lithiums in or 2 sodiums, which means we had to go away from iron, and we've switched to vanadium. I'll show you one slide later on, because vanadium can go from +5 to +3. So here's the opportunity. So whenever you have a challenge, it means you've got an opportunity, you can overcome it. So this just shows you the energy densities of commercial cells today compared with the theoretical energy density based solely on the active materials. Just look at what's inside that red circle. You'll see the actual energy densities are less than half, well less than half of what the theoretical is. In fact, they're about 25% on the volumetric basis. On the right-hand side, the same things on the weight basis. These are all about 25%. So there's a huge opportunity for us to increase that. Now, you can't go all the way to 100% because you've got electrolytes there, you've got casings and everything else, but we can increase it. And the issue I already mentioned, the carbon takes up half the volume. It takes up a lot of weight. It has to go. We need to put more lithiums in per transition metal. That'll increase it. And we need materials that have better electronic conductivity and ionic conductivity. Because remember, if you move ions in and out for a battery, you're moving electrons in and out. Many of these are not good electronic conductors. So those are the things we've been working on, and the major project to do that is the Battery 500 team run out of Pacific Northwest National Lab, and this is what we're discussing in detail the last 2 days. So this project uses pure lithium metal as the anode, and I'm told we've had minimal issues. There's been apparently one fire, and that's all, and it wasn't in the cell being used. It was a cell that had been put on one side and forgotten, and it caught fire one evening. So don't store batteries, and I'm sure every one of you has an old iPhone in your bottom drawer next to your bed or somewhere. Give those back, get rid of them, because they do go bad over time and they can catch fire. And I'm told in New York State, in Texas, you can throw them in the garbage. In New York State, that's illegal. But a lot of stores will take them back from you, so get rid of any old ones. So we use lithium metal here. We use a new electrolyte, an ether-based electrolyte, same as what Exxon used 50 years ago. So ether-based electrolytes plate out lithium much better. And I expect in materials science, you don't talk much about electrodeposition and metallurgy anymore. But issue with lithium is the same as with zinc. These materials like to form dendrites rather than nice smooth surface. So we're looking at that. We're increasing the energy density a lot, but I'll show you some issues there, and the costs keep coming down. The materials we look at have this meatball morphology. I think you can see it there. The primary particles are maybe 500 nanometers, 300 nanometers across. The secondary particles are up to 10 microns. And they pack well that way, and they get high surface area there for high power. But that brings you other problems. But just to show you the remarkable progress Battery 500 has made, and a lot of this is due to my ex-student, Jay, who's now at Pacific Northwest National Lab. Full-time she was, now she's half-time. She's now professor of, I should emphasize, mechanical engineering at the University of Washington. So I have 3 of my chemistry PhD students. One's professor of mechanical engineering at Washington, another one's professor of mechanical engineering at University of Colorado, and the third one's professor of mechanical engineering at Virginia Tech. And I don't know why they all go to mechanical engineering, but mechanical engineers must like chemists. But you can see here, we show you the number of cycles here. For year 1 is 2017. We got maybe 50 cycles, so you could recharge it 50 times. 1 year later, we got over 200. The third year, we actually increased the energy density. We pushed it harder. We got the same number. And today, with this material, we've got about 800 cycles, far more than you ever need in an electric vehicle. So we've shown you can make batteries with pure lithium with these ether electrolytes that will work. So we're going for longer lifetime, higher energy density, and I should emphasize, you see this says NMC 622. This means 60% nickel, 20% manganese, 20% cobalt. And initially, way back when, these were equal amounts. So we're up to 60%. To get higher energy density, we need more nickel. And this is the present status, now 80% nickel in these. And this is published in December 2023. And you can see we've got 400 watt hours per kilogram for over 250 cycles. No details here, because now we're above 350 watt hours per kilogram, which means it's export controlled. So we can't give a detail, they can't describe how they made these cells. In fact, we've got some of these cells now up to 500 watt hours per kilogram. So we can get high energy density, but we're getting fewer and fewer cycles as we go to higher and higher energy densities. And I should emphasize, these are all what we call pouch cells. You see a little cell here. The energy densities here are real. You may say, what do you mean by that? We weigh the cell, so it's everything in the cell. If you read the literature and somebody will say, we've got 600, 500, 400, look at the fine print. It'll either be active material or it'll be when extrapolated to a cell that's 10 times bigger than what we've got today. And this is a particular case with startup companies and some large corporations. So 90% of what you read in the literature is hype. So be very, very careful what's out there. So what is the issue? Why can't we have all nickel? This is a plot by South Korean folks, and maybe I can turn around and show you here. This is the energy or discharge capacity increases this way, and you see the nickel content is 50% or 30% here, up to 85%. So you get more and more energy, the more nickel you have in your system. But this vertical axis now gives the thermal stability. What do we mean by that? It means if we do a DSC study, like here, and just heat it up with the NMC and the electrolyte, and you see we get exotherms in here, and these materials start decomposing about 200 degrees. Centigrade, the best ones are about 300, and the best one here is a niobium modified one. But this is this plot, thermal stability on this axis. The more thermally stable, the less lithium, the less energy. So we've got this quandary here. We want more energy, but they're less stable. So we're trying to push the limits. We want as much stability as we can. Now, I should emphasize, our batteries will never go to those temperatures, but that thermal stability is the direct measure of how chemically reactive they are with the electrolyte. So we want high thermal stability. So how do we reduce the reactivity of these materials? Well, there's some obvious ways. Reduce the surface area. So any of you doing catalysis, you want lots of surface area to catalyze the reaction. Well, we don't want to catalyze the reaction with the electrolyte, so we want less and less surface area. You reduce the surface area, you reduce the current and the power, so there's a negative there. So we can go to less surface area, means go to single crystals rather than meatballs, or we can modify the material. Like this room, you paint the walls so they don't corrode. If you got steel on your car, it's all painted so it doesn't. So we can do the same thing with these battery electrodes. We can paint them with something. So we can surface treat them. We can also modify the bulk properties. So they react by the oxygen diffusing out. If we stop the oxygen diffusing, then we should make them better. So I'll show you just a few examples of this. Here is the typical electrodes used over the years. Left-hand side at the top is Exxon's titanium disulfide, large single crystals, very low surface area. Beneath that are Sony's lithium cobalt oxide. Sony realized these materials are hazardous, so they tried to make the crystals as large as they could. This particular picture is from Jeff Dahn, but the Sony ones were in fact 10 to 20 microns in size, the single crystals. I should point out the Exxon ones, in the basal plane, these crystals were more than a millimeter in size. But Exxon's ones work better than anybody else's for one simple reason. Titanium disulfide is a metallic conductor, so the electrons can get in and out very easily. The one I show at the top right is a typical one used today, these meatballs. So this is 60%. And beneath that is a trend we're having now. Let's go back to single crystals. And this is why my students made these single crystals. Number of reasons for reducing the reactivity. You get much longer life. And Jeff Dahn has used this 1,000,000-mile battery. I don't think any of you are going to drive 1,000,000 miles. But what this allows is for your battery to be tethered to the grid. So if you're at home, you can plug it into the grid. your utility can take power out of it, put it back in, or if you lose power, in the grid, it will keep your house going for about a week. So there's a lot of interest in that, and certainly the Ford Lightning, which is the first vehicle which allows you to do this without voiding the warranty. Encourages you, you go on the camping trips, you can plug everything into the truck and run it. The challenge we have today is how do we make large amounts of single crystals? It's not so easy. And I said these materials expand and contract by about 10%. If you keep the crystals below a certain size, about 3 to 5 microns, they will not crack. The meatballs always crack, because you can understand they're expanding by 10%. If one's like this, it tries to expand, it will crack all the joints between the others. When it cracks, then you get reactivity with the electrolyte there. So this is I6U single crystals, and you can see here's her capacity. It's dropped a little bit from the meatballs, but the capacity is very stable over 150 cycles. So single crystals work well. And there's a lot of work now around the world going to single crystals for commercial applications. Another issue in all these materials, these are layered materials. We can take all the lithium out, but we can't get it all back in at a reasonable rate. And this is the fusion cold reaction, controlled reaction. You can think of it just like this lecture hall. I see here and here, there's some seats in the middle. How do people get to those middle seats? Everybody has to move. So as soon as the lattice starts getting filled up, the diffusion coefficient drops by 1 to 2 orders of magnitude. And it's made worse because the diffusion mechanism is a die vacancy, so you need 2 vacancies. So we're trying to overcome that, but essentially all of these materials lose between 10 and 20% of their theoretical capacity on the first cycle, and you never get it back. So we've been looking at how can we change that, how can we increase the diffusion. And one thing we found out, modifying the surface of these materials does a lot to help, but modifying the bulk is even better. And I show you just some initial data we got with niobium. We looked at the whole range of these materials. We found niobium worked the best, partly because niobium is +5. It hangs onto those oxygens hard, so the oxygens can't easily move. And the other thing we found out when we put the niobium on the meatballs, or either after meatballs were formed or when we put lithium into them, a little bit of niobium went into the lattice, but some of the manganese came out. So the surface coating is a lithium niobium manganese oxide. It's not a simple thing. And we did this by a joint X-ray neutron diffraction study. And you can see on the right-hand side, this first cycle change. Just putting 1% niobium in there essentially eliminated half this first cycle loss. So we're gaining it. We don't fully understand it at the moment, but we're still working on that. And for this work, we got the Charles Hatchett Award. Most of you probably haven't a clue who Charles Hatchett is, right? Does anybody know who he is? He discovered niobium a few centuries ago. So we then said, okay, on the surface it helps us put the niobium on the inside. So now we've gone to 90% nickel, extremely reactive material. And by putting niobium into the lattice, again, this is just over 1% niobium. What it does, it stops the cracking of these meatball materials. You can see the large cracks, I think, here for the untreated material. There's little cracks in the coated material. This material now doesn't lose capacity over 300 cycles, even though it's 90%. If it wasn't treated, it would lose the capacity after about 10 cycles. So it does make a huge difference, just these little tricks, which metallurgists learned years ago to protect iron and other things. Aluminum protects itself by making its own aluminum oxide film on top. So moving on from layered oxides, where a lot of the interest is, we started with titanium oxide. The folks in British Columbia went to molybdenum disulfide because molybdenum disulfide is a naturally occurring mineral there. Okay. Then John Goodenough went to cobalt oxide, then lithium iron phosphate, and then the lithium vanadium. The oxides are still dominant because they have the highest energy density. Lithium iron phosphate is much lower cost because it doesn't have any cobalt in it, doesn't have any nickel in it, but it's a much lower energy density. Strangely, it has one of the highest rates of all cathode materials. Now, I'll get into that in the next slide. The other plus I've already mentioned, all those elements are available in America. Okay, it's safer. This material does not lose oxygen on heating, so it doesn't have its own source of oxygen inside. We're looking at, said the 4-volt manganese version, and we're now looking at the vanadium phosphate. I show you the plot here of the discharge curve. This is a plus and a minus. It's nice and flat, so the electrical engineers like that. But how do you know whether this is 20% used or 80% used? So if you read the Tesla's owner's manual, it'll say when you get home, plug it in every time to make sure it's full. There are now tricks you can use by mixing with other cathode materials to get more of a change at each end. But there's a challenge if you've got an absolutely flat plateau to know exactly where you are. So here is lithium iron phosphate. It shouldn't work. Phosphate's great electronic insulator, so the electrons cannot get in and out. It's a tunnel structure, so those tunnels should get blocked. Okay, it's a two-phase reaction. Unlike titanium disulfide layered oxides, where you can change the lithium content continuously. It's just two-phase, so you have lithium iron phosphate and iron phosphate. You could argue you have to nucleate a new phase. That should make things worse. But it's totally inconsistent with the actual behavior. It's the highest rate. We can use all the material. And strange thing in here, which we didn't understand for a long time, we have this voltage gap. So this, the open circuit on charging is different than the open circuit on discharge. Okay. That shouldn't be the case, so we had to understand that. And this is the phase diagram. You can see you got a bit of a single phase here and a bit here. This is two phase in the middle. So the trick in all this is, how do you make it work? It turns out you make it work by using small particles. So typically, if you're using lithium iron phosphate, it's about 50 nanometers. So the electrons can get in and out, and you use quite a bit of carbon to give it conductivity to the particles, and you substitute other elements into the structure, which then reduces this line to about down here. So we did studies on that. I'm not going to go into detail here. We wrote a whole review paper and chemical reviews on this. We had our Nexes EFRC, and half that EFRC was trying to understand how this worked. And we had theorists working on it, synthesizing people and characterizers. But we managed in the end to work out what was going on. The interesting one was, we said we need 2 lithiums. So we looked at a number of elements. Iron should work, if you can push it to iron 4, but iron 4 is about 5 volts. There's no electrolyte that's stable, so you can't use it. So we looked at vanadium, which we'd looked at many, many years ago, and we're told by DOE, yeah, but vanadium's toxic. Why are you looking at it? Stop working on it. Then about 10 years after that, they came back and said, why aren't you working on vanadium? So My students spent several years working out how to make this valdehyl phosphate. And this is a material that was first discovered by Alan Jacobson whilst he was at Exxon. These valdehyl phosphates are outstanding oxidation catalysts in the chemical industry, which means they also tend to react with our electrolytes. So there are some issues here. But she found out you can make these by what we call a hydrothermal solvothermal process. You mix all the ingredients together in water, or in this case, it was mostly alcohol with a little bit of water in there. And then you heat it, and it says 3 days here. All the students will know what's 3 days. It's a weekend. So they mix things together on a Friday, go home and take the reactants out on the Monday. We found by other methods we can get this up, but they found out that you make this nice tunnel structure, has protons in it, and then you can heat it to get the protons out, or we show you can, in fact, electrochemically pull the protons out. So you can make this nice three-dimensional lattice with tunnels in all directions so they won't block. And these are little cuboids she made on the left-hand side there, and on the right-hand side you can see now these are the discharge curves of vanadium 5 to vanadium 4, vanadium 4 to vanadium 3, and the first cycle is this one here. The 50th one is in the middle. So this behaves better, in fact, on the 50th cycle than the first one. So we had proof of principle. You can stuff 2 ions into a lattice with that lattice not being destroyed. So we've worked on this a lot. We have challenges making it in large quantities, and we have challenges of it wanting to react with the solvents in the electrolyte. The material itself is perfect. It's just as good after a few hundred cycles as at the beginning. And this is now several companies are working at commercializing this material. So let me get off the technical stuff and get into some of the other issues. It takes between 40 and 80 kilowatt hours of energy to create a 1 kilowatt hour battery. So they're not all that green, depending on what kind of energy you use. So there's a big issue, we have to solve that. Part of this is due to, as Elon Musk said, this poor little nickel atom travels 30 to 50,000 miles from the mine to the finished product, which is crazy. So we've been pushing hard. We need localized supply chains, which also solves some political problems. In other words, we don't want everything to be mined in country A, processed in country B, then all go to China before it comes back to us. So there's a lot of interest in having supply chains on each continent, which means the chemistry in the battery may be different on each continent, depending on what you had. We need clean, extractive metallurgy, so stop using carbon to reduce the oxides. Can we use electrochemical means or hydrogen or something else? And the other thing we have to do is eliminate what we're calling difficult materials. This means cobalt. Apple does not use any new cobalt anymore in any of its products. It's all recycled. So the cobalt comes from Congo. Most of that cobalt, or at least half of it, is child labor issues, and most of it's controlled by the Chinese. So a huge push to get the cobalt out. If we could make it work, a lithium sulfur battery would be the lowest cost, but there's nothing better than sulfur to be an ionic insulator and an electronic insulator. So there's a big challenges to get that work. So what we're trying to do is really saying there's no way we can catch up with Asia in making batteries. So the only way we can do it is by leapfrogging that technology, having better technology, different technology. So we keep complaining. In America today, there's lots of gigafactories being built, so we're building new old gigafactories. So the technology is the same technology as 20, 30 years ago. So we're saying we want to get out NMP, which is the solvent used to paint the electrodes. The older folks in the audience remember when a lot of paints were oil-based. They stank for days. Most paints now are water-based. It's the same issue with making the battery electrodes. You want to get those out. We want to ideally go to dry processing, so we don't use any liquids, and make thicker electrodes. So if we make double the thickness of the electrodes, we cut half the dead weight out. So less separators, less current collectors, so we'll make them thicker, but means we need better materials. So this is what some would call the circular economy for battery materials. We mine, then we convert the materials into what we want, then we make the cells. Then remember, these are organic solvents, so you need good system management so you don't overcharge or over discharge. This is why never buy a cheap battery from eBay. It may not have the electronic circuitry connected. It may be in there, so we take an X-ray, it looks good. So those batteries can explode on you. So, then we have the applications, then ideally we recycle everything so we can stop mining. So we went to the feds and to the state and said, no, let's try doing this. So pre-COVID, we went to New York State and said we want to build a large prototyping facility in our town. That was our Battery New York Center. They were on the point of agreeing to give us $50 million when COVID hit. Everything went dormant. But then Biden and the government decided to have these grants to build back better regional challenges. So we went into that using the New York State money for matching. And this is what we got. We got the facility, supply chain, workforce is a big issue. So we're training a workforce. This justice and equity has probably disappeared in the last month. And acceleration means startup companies. So between the two, we got $113 million there. We then got an SF engine, which allowed us now to do R&D. There was no R&D in the other one. So we got 4 universities working together. We got a whole group of companies at each point of this circular economy working with us. We got New York BESS, which is the industry consortium. And key to all this is you don't get federal money or state money without having the right connections, in our case in Albany or Washington. And we had an advantage because we had the Senate boss in our state at that time. And he came to the campus, I think, 3 or 4 times. Each time one of these started getting awarded, he'd come and wave his hand and say, this is what I did for you. But this has been extremely successful, and we're plowing ahead. We don't know what's going to happen now. But really what the future trends, I want to stop on this one, is lithium batteries is going to dominate no matter what you hear from other people. There's no moving parts. They're easily moved, no maintenance. So a lot of these grid storage facilities, a number in New York State, the operator can be 1,000 miles away. And look on this computer control, it flow systems, that doesn't work. So the only comment they make is the maintenance we have to do, we have to make sure the guy comes to mow the grass around the facility so there's no fire hazard if the grass gets dry or anything like that. There's a huge trend back to the iron phosphates. That's all available here. On the NMCs, the question now is how high should we go? But the other key thing is we want systems that operate over a wider temperature range. This eliminates thermal issues. And you've ever seen these grid storage facilities on a hot day, ask them to open the door so you can go inside. Lithium batteries like exactly the same conditions that every one of you like. So they're operated at 70 degrees Fahrenheit, most of those. If we could operate them over a wider temperature range, we can get rid of this air conditioning and save 20 to 30% of the energy, and they'll be safer. And I think I will stop there and try to answer any questions. Thank you.
Well, thank you very much for a fantastic presentation, fantastic talk, and I guess for inspiring all of the students. I think you're all ready to go and work harder in the labs, right? And have great ideas as to how you can solve the challenges that he just mentioned. Thank you, thank you. And I think we'll go for questions right now. We'll have 2 microphones and we can be on each side of the aisles here and I guess start asking questions.
I think we have one right over here.
Thank you for coming. This was great. Is there a known way to extract lithium without mining?
Yes. So, my ex-company, they're doing it by drilling. So I think they leased some 100,000 acres in Arkansas. So the salt, a few hundred feet down. So they're going to pump water down, pump the brine up, separate the lithium out, then put the brine back down. And they say, when they leave, you will never know they were ever there. So there's a lot of interest in this drilling type technology. And their advantage is they've got the deep pockets to do it. A lot of the startups will have difficulty raising the funds.
It's a very nice talk. Thank you very much. My question to you is about what areas of the battery we should focus on more, cathode, anode, or the solvents, electrolyte rather.
All of them. Because
No,
basically
you have done a lot on one side.
Yes.
What about the other side? That's what I'm asking.
So they all interact with each other. So battery 500, we kind of decided the last 2 days, we understand the layered oxides. Move our shift towards the interactions between the lithium metal and the electrolyte. Make sure we can plate out lithium metal efficiently and safely. So the battery 500 is going to shift to that side. They're also putting more effort on lithium sulfur. So we feel the layered oxides, we've optimized those. We can make them, manufacture them better, but the emphasis is going to shift to the anode side right now.
Hi, so I was wondering how you first became interested in research and how did you know that is something you wanted to dedicate your whole career to, and what would you say has been one of the most impactful moments of your career?
So I think most of you who are engineers or scientists, somebody got you interested in it. In my case, it was 2 teachers in high school. You've got to remember the British system is very different to the American system. So in Britain, your last 3 years in high school, you dedicate yourself, if you're a scientist, in my case, physics, chemistry, and math, and that's it. And so by the time you finish high school, you've done the first 2 years of college science. So in the case of chemistry, you've done general chemistry, you've done organic chemistry. And you've got good teachers, they've got you excited about it, you want to go to college and then study it. Similarly, when I went to Oxford, you study one subject. That's all, no gen ed, no this, that, or the other. So I went there to study chemistry. The big difference between Oxford and the rest of the US, you have one exam first week you're at Oxford, you then have one exam last 2 weeks after 3 years. No tests every other week, so you're self-motivated. And in the case of Oxford, you then have to do 1 year of research before you get your full degree. So you've got imbibed in research. I think it's very, very good because in that case, you spend 1 year learning whether you're excited about research or, I don't like that. And we used to run a pseudo REU program at Binghamton, run out by NSF in solid state chemistry. And we'd have about 18 undergraduates there, plus 2 or 3 faculty from smaller colleges. And of that 18, I would say 2 or 3, by the end of the summer, said, research is not for me. No, it's not a book. You do A, B, C, and you get D. So I think the key thing is you've got to do research early, see whether you love it. If you don't love it, don't embark on a 5-year PhD program. But bottom line is you've got to have people who've got you excited about it. And I had, physicist guy was called Squib Bowman, and the chemist was Major Lamb. And then at Oxford, I had Peter Dickens. At Oxford, you have weekly tutorials. He got me all interested in chemistry. And I should emphasize, in those times, chemistry and physics were dominant. Chemistry had 3 different departments. The inorganic department included crystallography and metallurgy. So all material science was, in fact, within the inorganic chemistry department. So you got that kind of materialsy side as well. And I just got excited about that. Then another fellow from Oxford had gone to Stanford. And towards the end of my PhD, I said, no, I'm going somewhere warm and sunny. And Stanford, Bob Huggins said, I'll take you to Stanford. And after that, maybe I think 7 or 8 more Oxford people went to Stanford. And the big thing I had at Stanford was Bob Huggins, after 2 months, I went there mid-January. By mid-March, he was in Washington running the MERSEC programs and Department of Defense. And he said, Stan, you're running the group for the next 3 years. So that was a huge opportunity to do what you wanted to do. And what I tell all students, if an opportunity comes up, grab it and run with it.
Thank you, Professor, for your nice talk. My question is, because there is a lot of time devoted at R&D level to the primary chemistry of cathode materials, and people don't spend a lot of time talking about, for example, doping and coating elements. And by the way, you mentioned about niobium, your work, this is one of the doping elements. So do you think that it's possible to have a more effort from the academia to understand? Because we all know that if you want to have a very successful cathode material, commercially speaking, the primary chemistry is not enough.
Yeah, there's no question. It's the same as semiconductor business. It wouldn't work without dopants. So we have to get into the depths of it. And what a number of us are trying to do is put modules together for faculty to use and students to use, explaining what batteries are, what the key components and parts of them are, and the roles dopants and other elements play in there.
Thank you very much for this talk. I just have one general question. So back in the 70s, you had little money, little resources, little workforce, and you got to invent the concept of intercalation. Today, after 50 years, we have more resources, more money, more workforce. And all the research is dedicated to improve the intercalation chemistry. And we see problems with the lithium. We want to move to sodium and other battery chemistries, but the concept remains the same. What do you think about this trend? Do we still need to keep improving the existing concept, or we need to completely invent a new concept to solve the energy transition? Thank you very much.
I think you have to do both. But what I tell students, don't follow the path everybody else is taking. Try to do something different. And it's particularly important if you're not at Harvard or Stanford or Berkeley, that you have to choose your niche where you're going to work. You can't compete with groups that have 50 to 100 graduate students. So pick something that excites you, something that's different to what other people are doing. And today, remember, you have computers, you have synchrotrons, you have all these tools which didn't exist in my day. So it's much easier to do things. The key thing I say to students, because we have a problem with students say, I'll try all these. I said, no. Think of an experiment that's going to help you in a particular direction. In the old days, we didn't have computers. We had to design the experiment. It took longer to design the experiment than to do the experiment. Today, it's just too easy to try everything. So really design the experiment to answer a specific question.
All right, I know there might be a few more questions, but so we have some time here. We'll have the reception outside, but let's thank our speaker one more time for a great talk. And again, you're welcome to join us out in the lobby for reception. Professor Whittingham will be around for a while. Maybe you can get a picture, ask a question, and kind of go from there. Thanks a lot.